In this lecture video, we are going to take a look at Le Chatelier principle. Please read the VR textbook chapter 13.5 for more detail. The Le Chatelier principle states that when a chemical reaction at equilibrium is disturbed, the system responds to minimize the disturbance to reach a new equilibrium. So what do I mean by that, right? So let's take a look at system A to B. Okay, so in this case, what you are going to see is that system A and B, let's say it's already at equilibrium. Okay, so if I disturb this equilibrium by adding more A, okay, so I'm going to add more water to A side. Okay, so I'm going to add more A. So the system is going to not be at equilibrium anymore, right? So the system is being disturbed. So in this case, because we have more A, so in order to reach the new equilibrium again, the reaction would shift, right? In order to decrease A to make more B, right? So in this case, you are going to see that the amount of A is going to be decreased, and over time, the amount of B would increase, right? In order to reach the new equilibrium again. Okay, note that the new equilibrium, as long as the ratio are the same. Okay, so these two equilibrium constant is going to be the same, even though the amount are not going to be the same as the original state, but still we are looking at the ratio, right? That's what the equilibrium constant tells us, is the ratio between product and the reactant. Now, another way that I can disturb this is by removing A, right? So I can remove A, take out A, right? So if I do that, you are disturbing the equilibrium. So therefore, in this case, you have less A. So the reaction is going to respond to this by producing more A, right? So B is going to convert to A, right? So the reaction would shift from B to A. Okay, so and then until the equilibrium established again. Okay, so all of this is part of the Le Chatelier's principle. Now let's take a look at example to help you understand this concept better. Okay, so this reaction right here is going to involve with cobalt complex with water that is going to produce pink color. Okay, if this cobalt complex with water react with chloride ion, it's going to produce cobalt chloride that is going to cause the color change to blue. Okay, so it's going to change from pink to blue. Okay, so and this is another product. Let's say that this reaction is endothermic. I'm going to show you the lecture demo to help you understand the Le Chatelier principle better. Okay, so I'm going to use this lecture demo to disturb the equilibrium of this equation. Okay, so I'm going to disturb it by changing the concentration and also changing the temperature as well. Okay, so that way you see it clearer. Okay, so let's take a look at the lecture demo. Hi everyone, in this lecture demo, we are going to take a look at the Le Chatelier principle. We are going to look at the system that involved with cobalt complex. Okay, so cobalt complex with chloride and also cobalt complex with water. These two have different color. The cobalt complex chloride is going to have pink color, and the cobalt complex with water would have blue color. And the mix of these two at equilibrium is going to give you the purple color, as you are going to observe here. Okay, so I have 6 test tubes that prepare with the identical substance. Again, in this test tube, the equilibrium already reached. Okay, so you will see that the mixture is contain both the pink and the blue substance. Okay, so in this case, you observe as the purple color. Okay, so the first test tube we are going to use as the control test tube. I'm going to compare the rest of this test tube when we are doing the change. We are going to compare to the control test tube. Okay, so we're going to compare the color against the control test tube. Okay, so the test tube 1, I'm going to pretty much disturb this by adding the chloride ion and see how the reaction would respond to that disturbance. And in the third test tube, we are going to disturb it by adding water and see how the change would occur. Okay, so the next one, we are going to remove chloride ion. Okay, the last two, we are going to take a look at the effect of temperature, one in cold temperature and the other is in hot temperature. Okay, so let's take a look at this together. First, I'm going to disturb this equilibrium by adding hydrochloric acid so that we add amount of chloride ion into the equilibrium to disturb the equilibrium. Okay, so I'm going to wear a mask with this experiment because I'm using the concentrate hydrochloric acid and I don't want to breathe it in. Okay, so let's take a look at how the color would change. Okay, so this test tube would be our control test tube. Okay, so this one would be the one that I'm going to add concentrate hydrochloric acid to it. All right, as you see here, right? So once we add more chloride ion, the reaction would shift toward making more blue. Okay, so that's the blue color right there. It's making more of the reactor. It's making more of the product. Okay. Next, I'm going to disturb equilibrium by adding water. Water is part of the product. So when I add water, it's going to cause the reaction to shift to produce more of the reactant, which is going to change to pink color. Okay, so let's take a look at this together. Okay, so I'm going to compare this again against the control test tube. Okay, so as you see here, right? So as water is being added, you can see that the color is changed to pink now. Okay, so the reaction is not mixing well. So let me actually mix this reaction real quick. So I'm going to add a little bit more. Okay, so I'm going to mix this reaction now. So as you see, right, the reaction now become pink. Okay, so as the equilibrium has been disturbed and is going to reestablish the new equilibrium again. Okay, so once it's established the new equilibrium again, now you will see that the color will become more pink than purple. Next, I'm going to disturb the equilibrium by removing the chloride ion, which is part of the reactant. So in this case, I cannot handpick the chloride ion out of the reaction. So what I can do is I can actually react with something else to remove the chloride ion. Okay, so the chemical that I'm going to react with is going to be lead nitrate. Okay, so lead nitrate will react with chloride ion and it's going to precipitate out of the reaction. So what you are going to observe is you are going to observe the solid that is going to precipitate out. Okay, so you are going to observe the solid color and you are going to see that the color change as well as the chloride is being removed. Okay, so again, chloride is the reactant. So as it's being removed, it's going to become more pink, right? Because the reaction will shift towards more of the reactant. Okay, so that white color right there, that's lead chloride, okay, that is being precipitated out. Okay, so that's how you remove chloride ion. Okay, so now as the chloride ion is being removed by precipitate out in that solid form of lead chloride, you are going to see that the reaction is actually going to be pink now. Okay, so let me mix this reaction real quick. Okay, so as you see, right, the color of the solution is now become pink. Next, we are going to take a look at the effect of temperature. Okay, so I'm going to use the first one as the control. Okay, and then the second one in the middle, I'm going to put it in cold water, and then the last one would be in hot water. Okay, so let's take a look at this. Okay, so here we have the reaction in cold water, and this one is in hot water. So here is the control test tube. Okay, so you probably see that the color is between these two, right? This is purple color. And as you see, right, when we disturb the reaction by reducing temperature or having the reaction at low temperature, at cold temperature, this one, you are going to see that the reaction would shift toward making more of the pink complex, okay? Versus the one in the hot water, you will see that the reaction would shift toward making more of the blue complex, okay? So now you see the effect of temperature. So here, when I show everything all together, right? So this is the control test tube. Okay, so this one is when the chloride ion is being added. Okay, so this one is when water is being added. This one is when chloride ion is being removed. Okay, so it's removing by precipitate out, right? So as you see, there is the solid lead chloride, white solid lead chloride is actually being precipitated out. So that's how you remove chloride ion. And then these two are when we disturb by temperature, right? So this is in cold water, this is in hot water. So from the lecture demo that you see when we add chloride ion, okay, so when you add chloride ion, and this ion coming from when you add hydrochloric acid, right? So the acid is an electrolyte, so it's going to dissociate into hydrogen ion and chloride ion. And this chloride ion is going to be adding to the reactant, right? So you are increasing the amount of the reactant in this case. Okay, so pretty much, let's take a look at this, right? So you already have the reaction at equilibrium, but you are disturbing it, right, by adding more of the reactant. Okay, so the reactant that we are adding is Cl minus. Okay, so you are adding more of the reactant. What would happen then? Well, you already see that the reaction would shift, right? So it's going to minimize this by reducing the amount of the reactant by producing more of the product. So that means in this case, these chloride ion that is increased is going to react with this cobalt complex with water. So that means in this case, it's going to, in order to reduce this, right, it's going to have to react with this reactant. So as these two react together, it's going to causing the concentration of cobalt water to decrease, right? So in this case, you are going to end up seeing that the reaction would shift to the right, toward the product. causing the color to change to blue, right? So that means in this case, as you see, right, it's going to shift toward the product, making the color to change to blue. The reason for that, because over time, right, as this decrease, right, in order to react with chloride that we have, right, it's going to produce more of the blue species. So therefore, you are going to see the color change to blue. Okay. So again, when you are looking at this, right, you note that the new equilibrium will still have the same value of the K constant as the old equilibrium. Okay, the constant is still going to be the same. Okay, so the ratio between reactant and product will still be the same. The reason for that, because we did not change the temperature. The next disturbance is adding water, right? So when you add water, we can see that water is part of the products. Water is adding to the equilibrium. You are ending up with more of the product, right? So in order to minimize the amount of product, the product would need to decrease, right, in order to produce more of the reactant. So therefore, in this case, the adding water is going to react with the cobalt chloride, right, in order to produce more of the reactant. So therefore, it's causing the blue complex is going to become less blue, right? And you are going to observe more of the pink color. So therefore, in this case, the reaction will shift to the left, right, in order to produce more of the reactant, right, to in order to restore the new equilibrium again. Okay, so you are going to, so that's why you observe the change of the color to pink. Okay, so until it's reached the equilibrium again. Okay, so again, the Kc value of this before disturbance and after the disturbance, the K value are going to be the same. The next one is removing chloride. As I mentioned in the video, right? So in order to remove the chloride ion, I don't have eyes to see which one is the chloride atoms, right? So we cannot handpick them. So in this case, in order to remove chloride ions, you need to react with something else. Okay, so in this case, we react with lead nitrate. Okay, so please note that this is not the correct lead nitrate formula, so it should be subscript 2 right here. So can you actually fix that for me? So lead nitrate, once it dissolves in water, is going to dissociate into lead ion, and this lead ion is going to react with chloride ion to form lead chloride that is going to precipitate out of the reaction. Okay, so as it precipitates out, it's going to cause the concentration of chloride ion to decrease, right? So in this case, you are decreasing the concentration of the reactant, right? So in this case, in order to reach the new equilibrium again, the reaction would shift to the left, right, in order to produce more of the reactant, right? So therefore, the color that you observe is going to become more pink. Now let's take a look at the effect of temperature change. Okay, so in this case, because this reaction is endothermic, okay, so endothermic means that when you are writing equation, you are going to add heat to be part of the reactant, because endothermic means the reactant absorb heat, right, in order to produce the product. So the heat would be part of the reactant. So in this case, when you are looking at how temperature increase or decrease, you are going to treat heat as part of the reactant, in this case for endothermic. Okay, so and you are going to predict the same way that you see earlier. So when we remove heat or at low temperature, right? So at low temperature, when the temperature decrease, the heat is being removed. So in this case, you are going to reduce the amount of heat, right? You are reducing the amount of reactant. Therefore, the reaction would shift toward making more of the reactant, right? So it's going to shift toward the reactant in order to establish the new equilibrium again. So you are going to observe the color to be pink in this case, right? And if the heat is added, right? So if heat is added, so now you have more of the reactant now, right? So in order to minimize this disturbance, right, it's going to shift toward the product in order to restore the equilibrium. Therefore, you are going to observe the reaction to become blue. Please note that this scenario right here, since we changed temperature, so therefore the value of Kc would also change as well. Okay, so the Kc value before the disturbance will not equal to the Kc value after the disturbance. The next thing is we're going to take a look at the effect of pressure on equilibrium. Okay, so I'm going to use the new equation. The reason for that is because the previous equation that we look at is involved with aqueous. Okay, so pressure doesn't have any effect on aqueous solution. So we are going to use the formation of ammonia to help us understand the effect of pressure better. Okay, so this reaction is exothermic. Now let's take a look at how we can change pressure, right? So let's say that we have this reaction mixture in this container. In order to change pressure, you are decreasing the volume, and that is going to cause the pressure to increase. Okay, so you can increase pressure by decreasing the volume. So in this case, whenever the volume is decreased, the pressure increase, you are going to looking at the number of mole of gas for the product and for the reactant to help us determine how the reaction would shift. Okay, so if you're looking at the reactant, okay, so all of these reactant together, you will see that the total mole of gas equal to 4, right? So 1 from nitrogen and 3 from hydrogen. And for the product, we have only 2 mole of gas for the product. Okay, so again, as pressure increase, right, we have high pressure. So therefore, in order to minimize this disturbance, the reaction would shift toward less mole of gas, because according to the gas law, right? So if you reduce the number of mole of gas, right, we observe that the pressure will also decrease as well. So that means in this case, in order to decrease the pressure, the reaction would shift toward less mole of gas. Okay. Now, if you increase volume, this is when the pressure would decrease. Okay, so when the pressure decreases, it doesn't have enough pressure inside the container. So therefore, the reaction would shift toward more mole of gas to produce more of the gas particle in order to increase the pressure. Okay, so in this case, we can conclude that whenever that you see pressure increase, the reaction would shift toward less mole of gas. If the pressure decrease, then the reaction would shift toward more mole of gas. Okay, so note that when you see number of mole of gas for the reactant equal to the product, that's when you are going to see neither forward nor reverse reaction favor. And again, please note that since this effect is the effect of pressure, we did not change any temperature, so therefore the Kc will stay constant. Now let's take a look at the application of the Le Chatelier's principle. Okay, so we are going to take a look at this in terms of Haber process. Okay, so Haber process is used in the manufacturing ammonium gas. Okay, so ammonium gas is very important because it's a precursor in so many things. Okay, so it can be used in producing fertilizer. It can be used in producing chemicals and other explosive substance as well. We are going to apply the Le Chatelier principle that we learned previously to help us looking at what are the conditions that helps to produce more of the product ammonia. So let's take a look at this example, right? So if we have this Haber process, okay, we want it to produce more of the ammonia, what are the conditions that we can explore, right, in order for this reaction to yield more of the product? Okay, so as we see previously, there are the 3 effects that we can look at in terms of causing the reaction to shift, right? So the one would be the pressure, right, because involved with gas. Second one would be the concentration, and the last one would be the temperature change. Okay, so let's take a look at the pressure. Okay, so the pressure, if we want the condition to produce more of the product, in this case NH3, what you will need to do in terms of pressure would be you will need to increase pressure, right? Because increasing pressure, the condition of the equilibrium would shift toward making more of the product, right? Because the product in this case has less more of gas. So in this case, one way to do this, or one way for this reaction to produce more of the product, is to increase pressure by decreasing the volume, right? So it's causing the reaction to shift to produce more of the product. The second one would be, well, if you want the reaction to produce more of the product, you can disturb the equilibrium by increasing the concentration of the reactant, right? So if you increase this reactant right here, right, you are going to causing the disturbance, right? It's going to minimize it by making more of the product by shifting toward the product, right? So you can either add more of the nitrogen or more of the hydrogen, right, in order for the reaction to shift toward the product. Or you can reduce the amount of product as well, which means that as the product is being made, you can actually remove that product out of the reaction flask, right? So that is going to cause reaction to produce more of the product as well. Okay. The third one is temperature. So since this reaction is exothermic, so the temperature would have an effect on this reaction as well. If you want, so because it's exothermic, right? So that means in this case, the heat is going to be part of the product, okay? Because the reaction is going to emit or release heat as the product. So in this case, you are going to treat heat as part of the product. So the temperature change, in order to make more of the product, you will need to decrease temperature, right? So you need to remove heat, so that way the reaction would shift toward making more heat. So in this case, in order for causing the reaction to move toward the product, you will need to reduce heat, okay, decreasing the temperature of the reaction. All right, this concept right here is actually being applied in how the scientists design, right, the reaction flask for the industrial production of the ammonia. Okay, so if you're looking at this picture, okay, so the gaseous ammonia is going to be available, right, because in the air, right, is available 78%, right? So that means this nitrogen gas is going to come from air. Hydrogen gas is going to be derived from natural gas. Okay, so these two gas are going to be feed into this reaction chamber right here. Okay, so as it goes through this reaction chamber, these two gas are not going to react yet. The reason for that is because according to the collision theory that we learned in chapter 12, right, the gas molecule need to collide with proper orientation and also with enough kinetic energy as well, right, in order to overcome the activation barrier. So that's why in this case, these two are not going to react yet unless they are going through this heating coil. Okay, so this is going to be heat up. It's going to heat up these two gas so that these two gas molecules have enough kinetic energy to react and overcome the activation barrier. Okay, so in order to produce the product. Not only that, this reaction chamber right here contain the catalyst as well. Okay, so the catalyst causing the reaction to occur fast, right? Because as we see in chapter 12, right? So catalyst is going to reduce or lower the activation energy by providing an alternative pathway, right? And also catalyst causing the reaction to achieve the equilibrium faster as well. Okay, so as the equilibrium is achieving faster and also reaction occur faster, it's going to eventually produce the product NH3. Okay, so all of these molecules have high kinetic energy because it's coming from this heated coil. It's going to travel up to the next part of the chamber. Okay, so it's going to go through this heat exchange coil. Okay, so as it travels, this hot gas right here is going to go to the next part of the reaction chamber, and you are going to see that it's going to be exchanged, right? And then it's going to go through this cooling coil. Okay, so this is going to be the part that is going to be condensed out. Okay, so the gas molecule that have high intermolecular force, for example, in this case would be NH3, right? Because going to exhibit the hydrogen bonding, the NH3 is going to condense out first because have the strongest IMF in comparison to nitrogen and hydrogen, right? So nitrogen and hydrogen are going to have only dispersion. So in this case, so the gas that is going to be liquefied out first is going to be ammonia. Okay, so the nitrogen and hydrogen will still going to be stay in the gas phase. Okay, so and this nitrogen and hydrogen gas is going to be fed or it would be recycled back into the reaction chamber again, and then that is going to continue into that cycle again. Okay, so these industrial production of ammonia is actually fit into the concept that we see earlier, right? So first, right, in order to causing more of the production of the NH3, right, we need to make sure that we have, one is high pressure, right? So, and the second one is high concentration of the reactant, which we do that, right? So the reactant is being fed, right? So you are increasing the concentration of the reactant and you are removing the concentration of the product, right? In order to causing the reaction to make more product, right? So the product is being removed by condensing out, right? So into the liquid form in this case. Okay. So again, this whole picture right here is going to represent the concept that we mentioned earlier. Note that the catalyst doesn't affect the K equilibrium. Okay. The second application of the Le Chatelier principle is can be used in carbon monoxide poisoning treatment. Now let's take a look at this, right? So when oxygen and carbon monoxide are inhaled, okay, so both of them are going to enter blood. Okay, so the normal red blood cell contain hemoglobin that would bind into oxygen that would carry to our cell, right, to deliver oxygen to our cell. But in the presence of carbon monoxide would tie into hemoglobin very strongly, 200 times stronger than oxygen. So that means in the presence of carbon monoxide is going to outcompete oxygen. So causing the cell to not having enough oxygen and causing the cell to suffocate, right? So in this case, in order to treat the carbon monoxide poisoning, we are going to take a look at the two relevant equilibrium. Okay, so whenever the patient suffer from the carbon monoxide poisoning, they are going to be treated with pure oxygen, okay, in order to remove carbon monoxide. Okay, so how would that work, right? So that's what we're going to take a look at. Okay, so the equation that we are going to take a look at first is going to be the binding of hemoglobin to the carbon monoxide. Okay, so this one is the free hemoglobin. Okay, so once hemoglobin see carbon monoxide is going to form this hemoglobin carbon monoxide complex. Okay, now the second reaction is going to involve with the binding of oxygen to hemoglobin. Okay, so when you have free hemoglobin, hemoglobin see oxygen into complex with oxygen to generate this hemoglobin oxygen complex. Okay, so let's take a look at these two equations together. So think about this with me. Okay, so the patient who suffer from carbon monoxide poisoning is going to have high concentration of hemoglobin carbon monoxide complex in their body. And again, the reason for that is because carbon monoxide can bind to hemoglobin 200 times better than oxygen. Okay, so now let's take a look at how the treatment would work. Okay, so think about this. At this point, we have high concentration of hemoglobin complex, right, with carbon monoxide. In order for hemoglobin to release carbon monoxide, okay, something needs to happen. Okay, so the first step, look at this. Okay, so first step, the reason why the patient needs to be treated with pure oxygen is because the concentration of oxygen will help the reaction to shift. Okay, so think about this. So by adding oxygen or by letting patient to inhale pure oxygen, it's going to increase the number of oxygen molecule. It's disturbing the equilibrium. Okay, so that means in this case, equilibrium being disturbed. So therefore, the system is going to minimize this disturbance by shifting the reaction toward more of the hemoglobin oxygen complex. But before I can do that, right? What is going to react with oxygen? Well, it's going to be the free hemoglobin, right? So it's going to require free hemoglobin in order to react with excess oxygen, right? In order to produce more of the product, hemoglobin oxygen complex. So therefore, in this case, by adding oxygen, is going to cause the reaction to shift toward the hemoglobin oxygen complex, and that is going to cause the concentration of free hemoglobin to decrease. Okay, so now because this concentration of free hemoglobin decrease is going to affect the first reaction, right? Because these two are identical. So as the concentration of hemoglobin, free hemoglobin decrease, is going to disturb the first reaction. Okay, so, and again, because the free hemoglobin decrease, therefore the first reaction is going to shift, right, to making more of the free hemoglobin. So as the reaction shift toward making more of the free hemoglobin, is going to require the hemoglobin carbon monoxide complex to be released. And this is how oxygen can help hemoglobin to release carbon monoxide, right, by disturbing this equilibrium. Now let's take a look at example 3 and 4. Okay, so these two examples, what I would like you to do is use the concept that we learned previously. Okay, so I want you to apply that and then answer example 3 and 4 yourself. Okay, so and then check your answer against my key. Okay, so I want you to practice this on your own. Okay. All right, so this is what we have learned so far in terms of the Le Chatelier principle. Okay, so we're looking at the change of pressure, the change of concentration, and also the change of temperature as well. Okay, so after this lecture video, please start working on your homework, chapter 13.5 as soon as possible.